Hi, so today we'll be discussing the paper Flash Attention, Fast and Memory Efficient Exact Attention with I/O Awareness by TriDAO. So overall, what does this paper do? It is an approach to make attention faster, 2x or 3x faster. Now there are a lot of other papers which claim to do that, but most of them are approximate methods, which approximate attention in some way. But this is an exact attention, meaning that the result you get from it is the same as the result you get from attention, the vanilla attention. And it is 2x faster and linear in memory complexity. Also, this approach has been widely adopted in a lot of frameworks. So all of your top frameworks now widely support this approach, so it has also got good adoption. So let's see how does it get these benefits. So yeah, as we know, transformers are slow and memory hungry on long sequences because the time and memory complexity of self-attention are quadratic. So in self-attention, you have a query of n cross d. I don't need to make this. We'll probably get this somewhere now. Yeah. So you have a query key and a value of size n cross d, where n is the sequence length and d is the head dimension. And to calculate the output, we have to calculate the attention scores q k cross t, which is n cross n, and this n cross n is the root of all problems. So this makes it quadratic in n. D doesn't really matter that much because D is very small. So like n might be 1024, D might be 64. Uh, this n cross n is the problem, and it makes the time and space complexity O of n square, which is very expensive when we have large values of n. N is the sequence length here, and we want a higher sequence length. So a sequence length is the input you give to your transformer. So bringing it to GPT-3 or ChatGPT, this is the length of the prompt you feed it into ChatGPT. So you, if you would want this to be large so that you can feed more information, and it has been observed that a higher context length leads to a generally leads to a higher performance because you are giving more information to the model. Uh, yeah, so equipping these models with larger context is difficult. They say that there have been a variety of. So this is not the first paper attempting to make attention faster. O of n square is what we currently have. There have been a lot of approaches which make this O of n log n, O of n uh, in complexity, but these are all approximate methods. And the paper divides this into two parts, mainly two approaches: sparse approximation and low rank approximation. Sparse approximation really says that if you have a query and a key, currently you you calculate the attention for each pair. So if this is n, this is n, you calculate the attention for each pair, which is n square. In sparse, for each query, you will only select a few uh, queries. So you'll only select a few pairs out of them, not all of the pairs. So this will reduce the complexity a lot. But this is approximate. You'll be trading off quality because you're not matching each query with every key. You'll only be approximating it with a few of them. So that is pass. Low rank approximation. So this, since this is an n cross n matrix, you can apply some sort of SVD or some sort of matrix factorization to make this into n cross m and m cross n, but there will be some loss which will happen in this also. So while it will reduce the complexity, it will also trade off quality. So all of these approaches usually trade off quality for computation. So they say they trade off model quality to reduce the compute complexity. However, this is a point which this paper is, they do not in most cases actually achieve a wall clock speedup. So what a wall clock is the actual number of time it takes to execute something on the CPU. So your complexity might seem to be O of n log n, but your wall clock might be 3 hours. And the wall clock of the normal attention of n square might be like say 3.2 hours or something. So you didn't actually gain much, even though theoretically your complexity is reduced a lot. And the reason they say this is most of these papers they focus on flop reduction, which does not necessarily correlate with wall clock speed, and they tend to ignore the overheads from memory access. So now this is where this paper is cool, and I love to read it because it goes into the hardware details of how a GPU is and how things are structured in the hardware, how are things used in the hardware. Uh, I'm not very familiar with this, but I'll try my best to explain it. So, okay, what is flop? Flops are floating operations. So this is the number of calculations you need to do. This is the number of arithmetic operations you want to do. A plus is one flop. A multiplication might be one flop or two flop. I don't know. I think a multiplication is actually two flops. But yeah, this is the total number of computations you need to do. So when you say that our approach is O of n square, it might have like, I don't know, 64k flops, which is very small actually. They have a lot of more flops. And if you translate it to ON, you might have like 8k flops. So this is why these papers say that, oh, we have very less flops, so our approach is much better. What they claim is that a simpler approach with 64k flops might take 3.2 hours, and a complex approach with 8k flops might actually again take 3 hours. Why does this happen? Because of memory and memory accesses and IO problems. Okay. Okay, so let's see how a modern GPU is structured. I don't know much about it, but let's see how much I can explain. So GPUs are not homogeneous. So GPU has a hierarchy of fast and slow memories. So you have DRAM, which is the main memory, which is huge. Something of the order of, it might even go more than 1 TB. Then you have a HBM, which is the high bandwidth memory, which might be something like 40 GB. Then you have SRAM, which is might be of 20 MB. But as you go from HBM to SRAM you get significantly faster speed. So HBM, the high bandwidth memory, this is what mostly we see. So when you say that you bought a 6 GB NVIDIA GPU, this is okay. Again, my PC is asking me to restart. Again, I'll ignore it. So this is what you get. If you say you have a GPU with 6 GB, this is what you are talking about, HBM. SRAM is, so if you see inside this, it is something like this. You have the HBM and you have multiple SRAMs. So they say here as an example, for an A100 GPU, you have 40 to 80 GB of HBM, which has a bandwidth of like 1.5 to 2 terabytes per second, and 192 KB of SRAM on each of the 108 SRAMs with a bandwidth of around 19 terabyte per second. So you don't have one SRAM, you have multiple of them. So like this says you have like 108 of, this is only one. This is huge but slower. This is smaller but faster, which is how memory works. If you have something which is huge and faster, then you'll obviously use it anyway. Uh, so what happens is usually you have some input which goes to HBM, and this is not where the computation happens. The computation happens in SRAM. As you can see, this has the compute. So there is a data transfer which happens from your HBM to some of your SRAM, as much as your particular input needs, or as much as how your code CUDA code is written. So yeah, this is how it works. But this transfer is very slow. So this transfer from HBM to SRAM is very slow, and this is one of the main bottlenecks, because they say that compute has gotten faster relative to memory speed. Operations are increasingly being bottlenecked by HBM accesses, thus exploiting SRAM becomes more important. What they mean is that, say you want to multiply a matrix. This might not be the best example. Say you want to do softmax. Say you want to do a softmax. So I'll tell you why it's not a, the first one was not a good example. But say if you want to calculate a softmax, this softmax calculation happens in this compute. This might happen very fast. It might take like point or 10 to the power minus 6 seconds. But to actually get the data, it might be taking 10 to the power minus 3 seconds to like get the data from HBM to SRAM. So while you can actually do the compute in 10 to the power minus seconds, you have to wait for 10 to the power minus 3 seconds to transfer the data from your HBM to your SRAM. There is this blog which explains it much better, is that your memory is like your warehouse and your SRAM is like your factory, and you are transferring data, you're transferring raw materials from your warehouse to your factory. So currently what happens is something like this, that uh, you send, like, currently there's this bandwidth cost, and this if the rate at which you supply materials is very slow compared to how the factory works, then the factory won't be operating at its entire capacity. Similarly here, if most of your time is being spent in data transfer, your compute might not be the actual bottleneck. And this is why if you only focus on flop, like flop is what happens here. Number of floating point operations happening in the compute. If you don't take into this data transfer overheads into account, then even if, because this is the main bottleneck, so even if you have like 2x more flops, but if you have like 6x lesser data transfer, your approach might be faster. Or if you have like 2x less compute, so this is being used 2x, like half of the time, but your data transfers are like 6x of now, because you have a complex data structure and it is accessing like multiple memory reads, multiple memory writes. It is not very optimized in the hardware implementation. Then you might make a lot of memory transfers, and that might actually make your approach slower, because the main bottleneck now is the memory data transfers, not the actual compute. Uh, Also, this will come in importance later, but uh, so this is a kernel. This is a kernel, and inside this it has a number of threads, a lot of threads, and each of these threads, some of these threads are grouped into warps. So these are threads, and these are grouped into warps. This will come in work later in FlashAttention V2, which made it even faster. But for now, I'll glide over it. But yeah, they say that GPU have a massive number of threads to execute an operation called a kernel. Each kernel loads inputs from HBM to the registers and SRAM, computes it, and writes it back to the HBM. So yeah, so these kernels are what read. They read the input from the HBM, compute it, and write the output back to the HBM. Why can't we have everything in the SRAM? Because there is not enough of it. We only have 20 MB, and we can't store everything in that. So next, so operations can be of two types, depending on the balance of computation or the memory access they need. They can either be compute bound or memory bound. So this is measured by arithmetic intensity, which is the number of arithmetic operations per memory byte access. But let's just think of it like, is your approach more focused on computation, or is it spending more time on computation, or is it spending more time on memory accesses? So compute bound processes which are compute bound are bounded by the arithmetic operations that are taking, and the accesses to HBMs are much slower. Typical examples of these are matrix multiplications with large inner dimensions and convolutions with large number of channels. This is why I said that matrix multiplication might not be the best example, because it is actually a compute bound process. Matrix multiplication, I am not very sure why this is compute bound and why other things are memory bound, but I'll assume that matrix multiplication involves a lot of operations. I'm not very sure how this happens, but let's for now assume that it is a fact that matrix multiplications are more compute bound. Whereas for memory bound, it is bound by the number of memory accesses, and they say that most of the other operations are memory bound, like element-wise methods, element-wise functions like activation, dropout, or reductions like sum, softmax, batch norm, layer norm. Most of these are memory bound. So most of the things which we actually care about are memory bound. And now this is the interesting thing. If you if you profile the vanilla attention, you'll see that this is the breakdown of the time it takes to do multiple operations to calculate the attention, and the matrix multiplication only takes a very less amount of time. This is the compute bound things, and these are the memory bound things. So most of your time is actually taken in doing this memory bound things, because the thing is, this might have a lot of flops. This will have a lot of flop as high here. So you would expect that it will take a lot of time to do this. It will take a lot of time to do this, and it will take the most amount of time to do this. However, matrix multiplication is highly optimized. So on your GPU kernels, you have special kernels to do matrix multiplication, and even though it is compute bound and it has a lot of flops, your hardware is so optimized to do it that it doesn't actually take much time. And most of your time is actually spent in doing these other operations which are bound on the memory. So yeah, that is one of the insights. And we'll talk about this fused kernel later. Or let's talk about it now only, because they also talk about it. So they say that the most common approach to accelerate memory bound operations is kernel fusions. If there are multiple operations applied to the same input, the input can be loaded only once from the HBM instead of multiple times, and some compilers automatically do this. However, in the context of model training, the intermediate values will still be returned to HBM to save for the backward pass, reducing the effectiveness of naive kernel fusion. What it means is that I think it is best explained from here. So, or let me explain it myself. Let me try. So, you have your HBM and you have your SRAM. There are multiple of these, but let's just say this. Currently, what we do is if I drag and drop this one here, no, oopsie. How does this work? Oh, oops. Anyway, if we see this here, this is the operations which we are doing currently. Yeah, I think this is the best way to do this. So currently what we are doing is to calculate the attention. This is what the vanilla attention does. You load query and key from HBM, you calculate the scores, and you write S back to the HBM. So you have your query and your key. This is your HBM. This is your SRAM. You send these to your query to your SRAM. You calculate the scores out of it, and then you send these scores back to your HBM. So 1 and 2. I'm counting the number of memory accesses you need to do. Then you read this calculated S back again to your SRAM. Calculate the softmax. Softmax. Let's call it L. And then you write, oh, okay, P. And then you write this P back to your HBM. Then you load your P and V back to your SVM, P and V, and you calculate O from it, and then you write O back into your HBM. This is what happens currently. You read and write back and forth. Now what kernel fusion does is very simple. You have query, you have keys, and you have your outputs. You are loading the query key, you are getting some output out of it, S. Then you are saving that S back to memory and then reading it again. Why do this? Why do these extra reads? Why not just calculate the softmax here? So this is say a kernel number 1, which calculates the S from Q and K. This is your kernel number 1, and this is your kernel number 2. What kernel fusion will do is it will create a new kernel K dash, which will take the query and key, calculate the S from it, and the scores from it, and also do the softmax in the same kernel, in the same SRAM. And doing this will save you these extra read and write. So you'll be fusing these kernels, you'll be doing the operations in one go, and you'll be saving a lot of memory accesses. So this is what kernel fusion is, and if you see, this is what FlashAttention does, is that it fuses all these kernels into a single kernel, and this gives it a good speed up. So yeah, that is one of the main insights of this paper, that you perform kernel fusion. This note saying that intermediate values need to be returned to HBM to save for backward pass, is the meaning of this is that for backward pass, so for training this model, you have to actually calculate the gradients. And for the gradient calculation, if you do it naively, then you'll have to store this S matrix back to your HBM. So if you know how backpropagation works, you sometimes store things in the forward pass to effectively calculate the gradients in the backward pass. So in a naive implementation, you'll have to store this S matrix in your HBM, and this S matrix is n cross n. This is the main one of the main bottlenecks. So if you are doing it naively, then you have to store this S matrix in your forward pass into your memory and then load it back again in your backward pass to calculate the gradient. And this might make it not so good for the memory. They This paper again circumvents this issue by doing some clever techniques. We'll come to that later. So this is another visual of this from this article, Deep Learning, Making Deep Learning Go BERT from First Principles. So currently what is happening is that if you have a lot of pointwise operators, which we do have in attention, think of softmax, dropout, activations, whatever, then if you do it naively, this is what happens. You send your input, you do a computation, you read your input, you do a computation, you write back your output, then you read it again, you do the computation, you write back again, and this takes a lot of time. Instead, you just, if you fuse the kernels, you just send the input once, do all the computation, and write it back again. So this saves a lot of time. So as they say here that in attention, most of the operations are memory bound because you have a lot of element like softmax or other element wise operations such as masking and dropout. So we have to do some optimizations for this. So this paper proposes two main optimizations, tiling and recomputation. Recomputation is mainly for the backward pass, and let's go over tiling first. So our main goal is to reduce the amount of HBM accesses. So to do that in tiling, what we do is we split the input into blocks, load them from HBM to SRAM, compute the entire thing in SRAM, and then write it back. So essentially we just somehow chunk the input in such a way that we can do all the calculation in the SRAM in one go and then write it back again. So this is essentially implementing kernel fusion for this. Uh, why we are chunking this into blocks? It is because we can't feed Q, K, and V into the SRAM in one go because it is huge. So we have to chunk Q, K, and V into blocks. And for each block, we'll perform the entire computation and in the SRAM and then write it back. So it might look very easy. Okay, yeah, you just chunked it and you did the computation and did it. There's a problem here because if it was so easy, then people would have done it. But the problem is your softmax. One of the problems is your softmax. So when you do softmax, it needs, so if you have a query and key and you calculate the score from it, this is n cross n, and then you do a softmax on top of it. So for a particular this score, to calculate the softmax for this, you'll need access to all the other things, all the other tokens in your sequence. And so if you just take this two things in a block, you can't naively calculate the softmax without needing these other things. So this is softmax couples columns of k. They obviously have a solution for it. They they figured out a way in which they can like calculate the softmax of a block independently and then combine them together to calculate the actual softmax. So this is demonstrated here, and this is from the softmax, the FlashAttention V2 paper, but it is the same as V1. So let me try to explain this. So the blue parts are in the HBM and the dotted parts are in the SRAM. So we want most of the things to happen in the SRAM. So this is block number 1 and this is block number 2. So first, these are two different SRAMs is what I understand. This is SRAM number 1, this is SRAM number 2. Because that is how you will parallelize it, is what I think. Or maybe it is the same as SRAM and you're doing it sequentially, I don't know. Most probably you're parallelizing it. So you calculate the scores for the first block, you calculate the scores for the second block, there's no problem. You calculate the softmax for the first block, you calculate the softmax for the second block. This is a local softmax. This is the softmax for these tokens and this is the softmax for these tokens. This is not the actual softmax that you want to calculate, which takes into account the entire tokens. Then you do a dot product. Okay, you do this and you also calculate some extra statistics. You calculate the L1, which is the sum of this thing, and L2, which is the sum of this thing and L1. So while you are doing this, all this happens locally, but you also uh, store some extra statistics. So you'll store the sum, and then once you have to calculate the output, this happens in the HBM. You calculate, yeah. I mean, the write happens in HBM. Probably this calculation still happens in the SRAM. So you will do A1 V1, A1 V1 upon L1. This would be your output for the first part. The output for the second part will need some statistics from the first part, and that would be L1 O1 upon L2 plus A2 V2 upon L2. So essentially what you do is that you do the calculations locally. You calculate the softmax locally. You store some statistics and then you rescale your output using those statistics in the HBM. So you can compute softmax locally and then do some clever rescaling so that the softmax is the actual softmax, the global softmax. And this allows them to like fit these blocks into their SRAM, do all the calculation in one go, like fuse all the kernels together and then get the output and like save on a lot of memory reads and writes. They show this here. So in the outer loop, this is key, query, and value. So in the outer loop, you take a block of a key and value. You copy both of them to your SRAM, and then in the inner loop, for like each of these, you go through all the queries and you copy the query block. This is a block to SRAM. You compute the attention, the softmax and whatever the attention, the final output, and you write it to your HBM. And this happens through this procedure, which allows you to calculate the global attention locally using local operations. So this is tiling. Tiling basically means uh, chunking your input into multiple blocks and processing each block. They go into a lot of detail into how this is actually implemented. I did not go through all of them. You can read the paper if you want to understand them in much detail, but on a high level, this is the idea. For the recomputation is for the backward pass. So what this says is that to calculate the gradient, you need S, which is n square, which is prohibitively expensive. So one of our goals is not to store the O of n square values for the backward pass. The backward pass typically requires S and P. P is this is the score, this is the softmax to compute the gradients. However, what they say is that if you store the output O in the forward pass and some statistics, then you can recompute S and P easily in the backward pass inside the SRAM itself. So when you are doing the backward pass, if you store this output, if this is stored in your HBM, then during the backward pass, you can efficiently calculate S and P. I mean, P is this, I think. There is some notation difference, but you can efficiently calculate S and A in the SRAM itself and use it to calculate the gradients. You don't have to store this n square into your HBM. You don't have to store your S into your HBM. You only need to store O into your HBM. O is n cross D. Output is n cross D. So you only need to store your output. And in the backward pass, you load this output and your query key and whatever. And on the fly, you'll again recompute your S, and this will have some increased flops, like flop, so you'll be doing some more computation. But since the main bottleneck is the memory bandwidth, memory accesses, you'll actually be faster. So yeah, so they say that this is, so even with more flop, our recomputation speeds up the backward passes due to reduced HBM accesses. This is similar to gradient checkpointing, uh, but in gradient checkpointing there is a trade-off between speed and memory, but in this case the computation is structured in such a way that even if you are getting more flop due to the recomputation of this scores and whatever, since most the actual bottleneck is the memory accesses, you are making it faster. Also, this is the part which this reduces your memory complexity from O of n square to O of n, because you're not needing to store this entire s square into your memory. You're only storing your output, which is O of n. So yeah, these are the two main components of flash attention: tiling, which is dividing the input into blocks, and so that you can like fuse the kernels and do all the computations in the SRAM itself to speed up things a lot, and recomputation, which is for the backward pass, for doing backward pass efficiently and without having to store the O of n square matrices. So yeah, these are the main two things of flash attention. Okay, so now let's see some analysis of the IO complexity. So if you see this table, this compares the standard and the flash attention. So if you look at the flop, the number of computations you have to do, flash attention has more computation to do than standard attention. This is because of the recomputation in the backward pass. You have to do more computation. You have to compute things again, so there is more computation happening. However, the HBM accesses, the HBM read and writes, are significantly less. So this is the memory thing which you're accessing, and this is the main bottleneck. This is the memory accesses we are doing, and this is the main bottleneck. So if we are doing less memory accesses in flash attention, it is faster, which can be seen in the runtime, which is the wall clock time. So the runtime of flash attention is significantly less compared to standard attention. So yeah, this is cool. Next, in this figure, they see the effect of the block size on the speed up. So as we increase the block size, the number of HBM accesses decreases, because if you see here, we copy a block from HBM. So, and we have to copy all of these blocks. So if the block size is larger, we'll have to copy lesser things from the HBM. So lesser access to so a higher block size would lead to lesser accesses to HBM, and so the HBM accesses are reducing, and correspondingly the runtime is also reducing up to a certain limit. And they said that after a particular limit, the runtime is actually bottlenecked by other factors, arithmetic operations and stuff. So not the memory, but some other factors become the bottleneck, and so we don't like see this runtime reducing after a point. And also after a point, the block won't fit in the HBM. So if you, so like in the Most extreme case, you could argue that we can take a block size of the entire sequence and fit it into the SRAM. That would be the fastest thing to do, but that won't fit into your SRAM because your SRAM is tiny. So yeah. And this third one is for block-sparse. So yeah, block-sparse is not much. It is adapting the sparse attention approaches to flash attention. And in that, we have a sparsity mask. So essentially, in the query key, in the score calculation in the query key, currently for each query, we are calculating the score for each key value. In sparse attention, you only calculate it for a few of these keys given on the sparse matrix you have, which shows the connectivity. This reduces the computation and the cost and stuff. Uh, However, this is an approximation because ideally you'll have to, like for an exact calculation, you have to take all the keys into consideration, which is what flash attention does. But sparse attention, you trade off quality for compute. And if you use a similar thing in flash attention, they can say that you can make flash attention even faster. Obviously, you'll lose on quality a bit, but you can make it even faster. And they say that if you see, it is like you can make it faster by a factor proportional to the sparsity. So this is percentage of non-zero blocks. So 20% means that only 20% of the pairs are being taken. 60% means 60% of the pairs are being taken. So you can see that this is a linear speed up you get based on the sparsity. Obviously, this would be less accurate and this would be more accurate. So there is a trade-off between accuracy and uh, the runtime. So their point was that you can integrate these sparse attention approaches easily into flash attention and make it even faster. Now looking at the results, first they show that they can train models faster using flash attention, and on a particular MLPerf benchmark in which you have to train a BERT-large model to reach a particular target accuracy. Their implementation is 15% faster than the top implementation. Uh, if they integrate flash attention into GPT-2, they can get up to 3x or 1.7x speedups depending on what implementation they are using. They also test on a particular benchmark called long range arena. I'm not familiar with this, but uh, basically again flash attention is the fastest here. It has a 2.5x speed up to standard attention, and the block sparse flash attention is faster than all the approximate attention methods that they have tested. So this block sparse is faster than all of these methods. These methods are the approximate attentions methods which we are comparing with, and the block sparse one is the fastest. And the flash attention one also gives a very strong competition. And this is the most accurate one. Or this is, yeah, I think this is the most accurate one, 59.8. Yeah, this is the most accurate one because this is the exact attention. Also, you can, since you have now sped up your model and also reduced memory complexity to linear, you can train on longer sequences. So they say that they were able to scale the context length of GPT-2 by 4x while still running faster than the original implementation, and they achieved better results out of it. They got a 0.7% better perplexity while being 30% faster, and similar results hold. They get higher accuracies because of a higher sequence length enabled due to a faster method. Then they show some benchmarking comparing the runtimes and the memory usage of this approach compared to other approaches, and TLDR, it is the best thing to do. So the limitations and future directions, The major limitation they said was that for implementing this, they had to write a custom CUDA kernel, and like that is hard. You can't always do that, but this is not such a limitation right now because uh, PyTorch, TensorFlow, and all these have already integrated this flash attention into their core library, and also there are there is a library called Triton to write custom CUDA kernels in a high-level language. So yeah, not much of a limitation, but yeah, still you have to implement these things. Involve implementing low-level CUDA kernels, which might not be possible for everyone. But yeah, that is what researchers are for. They also say that while attention is the most memory-intensive computation, we can apply these similar concepts to other layers also. So they say that in future work, you can like sort of apply these memory-aware things to other layers as well and make them even faster. Also, applying these to multi-GPU settings is even a further scope for future research. So there was a follow-up to this paper, which was called FlashAttention V2, and uh, basically it is again 2x. It has some optimizations, which makes it 2x faster than the previous version. And how do they mostly do it? It is a lot of hardware optimizations, which I barely understood. But going over this thing, the first speed up was fewer non-matmal flops. So in your attention calculation, you have matrix multiplications, but you also have non-matrix multiplication things, which are not easily converted into matrix multiplications. Matrix multiplications are fast because uh, GPUs have specialized units which are specially designed for matrix multiplication, and matrix multiplication is very, very fast on that. So, as an example, they say that A100 GPU can do 312 teraflops of matrix multiplication, but only 19.5 teraflops of non-matrix multiplications. So you can sort of say that each non-matrix multiplication flop is 16 times more expensive than a matmal flop. And so they somehow reduce the non-matmal flops in the approach. And they say that one way in which they do is in the softmax strip, they reduce the number of rescaling operations and bound checkings and other stuff. So I think this rescaling bit, they reduce the number of rescalings they do in some way to reduce the number of non-matmal flops, which are very expensive to do and thus giving a speed up. Then they have a better parallelism. They said that the first version of flash attention parallelized over the batch and the number of heads. So in attention, you have batch size, you have in multi-headed attention, you have for each attention head, you have a batch size and a sequence length. So your input is batch size cross sequence length. So in the original version, they parallelized over the batch size and the number of heads. So each thread block was running one attention head, and overall there were batch size into number of heads, number of thread blocks, and each of this thread block runs on a streaming multiprocessor. So if you have 108 of them, this is good enough. And you have 108 of them, so this is okay if you can like if this number batch size cross number of heads is greater than 80. But if you have a longer sequence, so let me go back to the OneNote for this. Your input is batch size cross number of heads cross sequence. Each of this runs on one of your SRAM, and you have 108 of these. You want to occupy all of them because you have compute, so you want to occupy all of them. So they say that okay, if you have a high batch size and a high head count, you can do this well. But if you have a high sequence length, because currently they're in FlashAttention V1, we are only parallelizing over this. We are not parallelizing over this. But if you have a higher sequence length or higher context length, which is all the paper was about anyway, if this number is very high, then you can't have a very high batch size and a very high head count. So if this was multiplying to be 120, say, and initially these were like this was 2 and this was 60, so say 30 and something like 2. Okay, so you had 60 of these and you were able to parallelize 60, which is fair enough. But if you have a sequence length of 60, then you'll only have uh, one batch and say two heads and a sequence length of 60, and so you'll only be able to parallelize two of them, and you actually have 108 of these cores, so you'll be missing on a lot. So in flash attention V2, they also parallelize over the sequence length. So this is what they say. We additionally parallelize over the sequence length dimension. This results in a significant speed. Now, even within a thread block, they have to determine how to partition the work between different warps. A warp is a group of 32 threads working together. So they say that we typically use 4 or 8 warps per thread block, and the partitioning scheme is like this. And they sort of change this partitioning scheme to reduce the synchronization and communication costs and to speed up basically. This is a very low level detail, but so a warp is a group of threads in a single SM, in a single streaming multiprocessor. So a streaming multiprocessor will have a thread block, and a thread block will have multiple warps in it. And some of those warps, so they say that they typically use 4 or 8 warps per thread block for this, and they're partitioned in this way. So in the original version, so the blue things show things which are accessible to all the warps, and the red ones are split across different warps. So in the original version, the query was shared across all warps, and the key and value was uh, split across different warps. So this is called the sliced case scheme. And they say that this was inefficient because there was a lot of synchronization that needed to be done for the intermediate results. You had to calculate everything and then store one by one to the value. Like you have to do this one by one and then again do it one by one with the value, and like there will be a lot of communications in this. In Flash Attention V2, however, they flipped this across, and now the queries were split across the warps and the key and value were shared across the warps, and they saw that this reduces the number of computations you have to do, and so this was faster. Again, this is a very low level optimization, so they are going like in the previous paper they focused on the HBM and the SRAM, and they wanted to push more things to the SRAM. Now they're looking inside the SRAM and seeing how you can optimize the computation inside the SRAM even further by looking at the threads which make it up. So yeah, it is quite complex. Uh, Other than that, they say that flash attention only supported head dimensions up to 128, but now flash attention 2 supports head dimensions up to 256. Also, it supports multi-query attention and grouped query attention. I don't know what these are, but it says that you can multiple heads of the query attend to the same key and value in order to reduce the size of KV cache during inference. This is probably some other optimization which happens, so they support that as well. And then they have this benchmarks in which they say that okay, our approach is like 2x faster. So yeah, this was the flash attention V2 thing on a high level. I know I haven't covered it in much detail because I don't understand it very well, but I hope it serves as an overall guide to what happens on this on a high level. So this is the GitHub repository for flash attention. This is what the code is, and yeah, this is implemented. People have also implemented, like had their own implementations on this of this. Uh, so there is this library called Triton by OpenAI where people have implemented this. And Triton, yeah, so Triton is supposed to be a high level language for writing efficient CUDA kernels. So instead of writing very low level CUDA kernels, you write it in a Pythonic version, and it automatically like converts it into a very efficient CUDA kernel. So someone wrote a CUDA a Titan implementation of Flash Attention, and then they have this page which shows that where all Flash Attention has been used, and it has been used a lot, so a lot. So it has been integrated into PyTorch, Hugging Face, DeepSpeed, Megatron, Mosaic, Eleuther, then MLPerf, Diffusers has it. This is where I originally got to know about this because I was implementing some model and it had flash attention in it and there was some bug and something happened. So there are a lot of it has been adopted a lot by the community because why not? It makes things 2x, 4x faster and it is exact. One of the problems right now is that it is not supported by all the GPUs. Currently, it is only supported by few of the NVIDIA GPUs, but they'll probably get over that because they say here there's only support for these particular GPUs and up to a particular head dimension. So there are some constraints. It's not a silver bullet, but overall it was a it was a trick which made attention much faster for everyone using them, and it was widely adopted. So I think it is a very cool paper, and like it is important to do work like this which makes things faster and cheaper. And I also loved that they in- integrated the knowledge of how these things actually work in the hardware. People often forget that these algorithms run on the hardware. So integrating the knowledge about the hardware to make these algorithms go faster was very cool. So overall, it was a very cool paper. And yeah, thanks for watching.